area. Now, in chapter 5, understand that we used area to find what an integral was doing. We had geometry formulas for area that we were using all the time. But in chapter 6, we're going to use integrals to find area. We had to first understand what they actually did and what they would find, and now we're going to use them. So, area between two curves. And I think it's important that you learn a bit about the notation. If you look down here, this is saying region S is the set of all points, all xy coordinates, such that while x remains between a and b, y remains between g of x and f of x. So that's defining this region in here, and you need to learn this notation because it's going to show up here and there. And it's proper math notation on top of it. So what I want you to realize is if I draw straight vertical lines, if I looked at what is this y value, maybe it's 5. And what is this y value? Maybe it's -2. If you wanted to find this vertical distance, you would do 5 minus -2, right? So you're taking the top y value and subtracting the bottom y value. If I go over here and I look at this vertical distance, let's see, y is maybe 5.2, I don't know, for the top. On the bottom, say y is 2.3. You're going to take that 5.2 and subtract the 2.3 to get this positive distance. At the moment where one of the functions crosses the x-axis, if you at that moment looked at what is y top minus y bottom, you would just get the y top. So I want to point out to you that it doesn't matter where the graphs themselves are located as far as the x-axis is concerned. They might be both above the x-axis might go between one or both of them, or they might both be below the x-axis. Either way, you will get a positive number if you always subtract in the order of the top y value minus the bottom y value, even if they're both underneath the x-axis. So just to make sure that you're clear on that, let's say this creates the top curve and this is creating the bottom curve. If I integrate y top, I'm getting this negative area. But then when I subtract y bottom, I'm adding this because I'm subtracting the negative number and ultimately getting this as a positive number. So always top minus bottom. And here's a lovely picture of our approximating rectangles. And now the official. And then an emphasis with a picture, but looks like I can't show both of those nicely at the same time. So area is defined as the subtraction of those two functions between x equals a and x equals b. And I want to point out to you that the f of x minus g of x is just a length. The dx brings in another dimension with width. If I'm going to get area, I have to multiply 2 dimensions to make it happen. I want to remind you that we are not solving our integrals through the whole limit sigma thing. Could you imagine how crazy that could get? Absolutely horrible. We are going around that. And instead of doing area, we're doing antiderivative. Because we've got formulas for derivative, so all we have to do is go backward on those formulas. When we do that, we don't see the impact of that differential dx. It feels like it's there for no reason and no purpose, but realize we are taking shortcuts. It happens. I had, was it last week? I think I had my bad morning. Maybe it was this week earlier. I don't know. Anyway, so very, very important to understand the key role that dx plays. Without it, this does not make sense. And we are creating little slivers of area. I like to call them area slivers. They're tiny, tiny, tiny little pieces of area that I then add together to create something of substance. But I can't just add one-dimensional lengths together and say that's area. All right. Are you ready for an example? Of course you are. So here's a first example. Now, normally I do this this chapter with half calculator, half no calculator. As far as testing goes, I can't know for sure whether you are going against my wishes and using some kind of graphing device. So I've got to figure out how I want to cope with that. It's very important when you go through this without a calculator, you're gaining skills that you are expected to have. If you do this only with a calculator, you will not get everything that you need. You've got to look at some things. How do you do this by hand and remind yourself of how the math works? But also you have to learn how to do this by calculator. If you are not planning to take the AP exam, I'm not sure that we're even going to have an in-person final. That's another thing I'm going to have to cope with. But basically, if you are planning on taking the AP exam, you need to have your own graphing calculator, and I need to warn administration about it so that they know where to get those graphing calculators. But you've got to have a graphing calculator for this chapter. However, there's other technology that you can use. If you're not taking the AP test, don't spend money on a graphing calculator. It's not worth it. The only reason you need that calculator is because of testing purposes so that you aren't on a computer. That's really the only reason anymore. The calculators are slower than the computers. The only purpose for these things is to make sure that you're testing without going into other areas of the internet. Anyway, so draw this. Not necessarily. F of x and g of x don't have to be defined as f is the top function, g is the bottom function. You just want to determine who is the top, who is the bottom, and not worry necessarily about the name. or the letter given. You're going to draw this without a calculator. So you're remembering, what does e to the x look like? Whee! How does y equals x go? Whee! And between 0 and 1. And if you draw a bunch of vertical lines, that'll show you the region and also kind of show you the rectangles while you're at it. So you're going to set up an integral that will find that area. And you have the length of your rectangle. And you also have a teeny tiny width, which is dx. So the top function is e to the x. The bottom function is x. And we are only going between x equals 0 and x equals 1. Whatever variable that differential uses, that tells you who this is the boundaries for. These are the boundaries that x will get to exist within. So you're going to write the integral down, then you're going to solve the integral and go, yay! And that's about it. So integrate e to the x, integrate x, plug in 1, plug in 0, e to the 0 is 1, so we end up getting e minus 3/2. Not a very big number, but we didn't expect it to be big. If you look at how small that region is. And then I have a nice little clip from the textbook because they have a computer drawing as opposed to my by hand drawing. All right, are you ready for another example? Here's example number 2. Without a calculator, draw these two graphs. And you have to figure out where they intersect each other. Again, without a calculator. So everyone's drawing right now. My dog likes the pause moments where I let you get work done. He's getting some attention. Yes, don't you, baby? Oh. Yay, I love COVID. For the second parabola, you should notice that it's an upside down parabola because of the negative leading coefficient. If you factor it, you can find its x-intercepts, and it'll save you a bit of time because those x-intercepts give you one of the intersection points. And you know the vertex is halfway in between, and I just realized that I don't have a to-scale drawing the way I did that. I need to go out a little farther for 2. Now it's just starting to look horrible. Anyway, my x-intercepts, and then vertex is at 1, and if you plug 1 in to see what the y-coordinate is, you find out it is 1, which is the actual y equals x squared y value as well. So your drawings may not be spectacular. You just need to draw so that you can see what is going on. You can see that the x coordinates of intersection are 0 to 1. And then your integral to give you area is length times width. And you want the positive value of this length. So top function is the 2x minus x squared. The bottom function, x squared. So on a test, you're expected to write the definite integral and then solve the definite integral. The amount of drawing that you do is really more for yourself. I don't grade your drawings. So let's have some fun and integrate. Oops. There we go. So we get the gargantuan area of 1/3, which would be expected. And it looks like people are still writing. But I'm going to keep moving. And I do have the textbook shows the answer as well with a very nice picture. And you can look it up there. Now, dun, 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 get out your calculator if you have one available. And problems usually don't say find the approximate area. They say find the area of the region bounded by the curves. So I want all of you to type these functions into your y1 and your y2 in your calculator. The TI-84s are the ones that I explain how to use. So know that if you get anything that is not a TI-84, you're going to have to figure out how to use it. And TI is Texas Instrument. As far as online tools, Desmos works really well, but it won't, at least that I know of. Maybe I should check out to see if they've added a feature for finding area. But I know there are some online things, and I can look it up and see if I can find something online that'll help you do the same thing the calculator does. For the purpose of the AP exam, I want to make sure you know how to use your calculator. You will likely be doing social distance testing in person, and you will have to have a calculator and know how to use it. So, let me clear that out. While you guys are typing this into your calculator, I'm giving you a little bit of time. When I first graph these functions, this is what I see. And I would like to zoom in. To zoom in, do you see the zoom button right there in the middle, right under the screen? Zoom right in the middle. You can zoom in. If you push the zoom in button, I'll show you what you see. It looks like nothing changed. But do you see that there's a cursor that's acting a little differently? Use the arrows. Use the arrows. Move that cursor to where you would like to center your zoom, and then push enter when you are in a place where you like. So I'm got a place that I like, and now I'm pushing enter. And if I want to zoom in more, I can continue to move my cursor, and you see it's still acting weird. I can push enter on it again if I like and zoom in even further. So you are expected to know how to use a calculator and change your graphing window to suit what you need to look at. Also know that if you do anything through the calculator menu, the entire thing you are using has to be active in the window you see, or it won't calculate it. It will only calculate with the window that you are on for anything you ask it to do. So I'm going to zoom out because that's too far. Okay, now, can everyone see that they definitely intersect at the origin? You need to find the other intersection point. And I'm going to grab a Desmos graph of this. On the calculator, after you have graphed, you're going to go to the menu that is with the F4. So second, and then the F4 button is the calculate menu. So second and the F4 position. In that, it has intersect or intersection. It's number 5 down that menu. And I need to show you what happens when you push enter. So, boom, I'm about to push number 5. Now, do you see the first thing it's doing? It's saying lower first curve. If you push enter, it puts a notch on it and automatically puts you on the next one. Push enter again, puts a notch on that one. Now it says guess because there could be more than one intersection point. With your arrows, move your cursor near the point you're trying to find the intersection. You don't have to be insanely close. Just get kind of in the vicinity and push enter. And here we go. And it tells you the X and the Y coordinate of that point. You only need the X coordinate. Now, what's the joy of Desmos? If I click on either one of these two and then just hover over my intersection point, wham. So, computer technology will do things much faster than a calculator will. Now, it is your job to write a definite integral. And I'm going to go back over here. Now, yes. Before I have you touch your calculator to do anything else, and yes, those are important things. This X coordinate, you have to write it down at accurate to at least 3 digits after the decimal point, but there's a kicker. You also have to use this intersection point in a definite integral to find area, and your area must be accurate to 3 digits after the decimal point also. If you just put in 3 digits after the decimal point for your X coordinate, it may not be good enough, and you literally could be off on your third digit. And you don't want that. So are you paying attention? Very, very careful attention. Okay. Right now, I haven't touched any buttons since I found intersect, and I'm going to quit to my home menu. Actually, I wonder if I could just, I wonder. Hold on a second. I just suddenly realized maybe I don't have to go to that window. Nope, I do. Okay. So you are going to push second quit, and you're going to go to your home menu. Okay. You have a store button, STO, right there. You're going to push that stow button. And I have found that it does not automatically give me the alpha button. So if you look at the cursor right now, it's just blinking. That's not in alpha mode. I need it to be in alpha mode. So I'm going to push alpha, and now the cursor is a blinking A. Pick your letter. Doesn't matter what letter you pick. You've got green or whatever your alpha button color is. You have letters that match it. Pick the letter you want to use. Push on that and push enter. Yeah. How do you do? With the Inspire, do they have a store button? Okay, just push the store button. You'll know if you've put it in. And I think you can just push a letter because you've got a whole non-QWERTY keyboard. Do you know why it's not a QWERTY keyboard? Because it would be easier to type if it were a QWERTY keyboard.
Because the AP test, the College Board bans having a QWERTY keyboard on any graphing calculator.
Yes, because they're afraid you're going to type up all the answers. QWERTY keyboards were banned, and then Texas Instrument figured out that they could just put it in alpha order and it was okay. It's all about the test. Anyway, so was everyone able to store that? When you push enter on that store, it tells you that you have stored it. So what you're going to see the AP test do is they're going to write their answers where they're going to give that intersection a letter. So they'll say the intersection. And I'm also going to do this. I'm going to say that they usually will name the functions. So I'll just say they named this one f of x, and they named this one g of x. And you need to tell them that you found the intersection of those two. And then you only have to write a certain decimal point accuracy. And now I forget what the number was. Yeah, 1.181 is rounded and good enough. Thank you. Eh. Now what you can do is you can temporarily call that a letter. I'm going to say it's B. You can then, when you set up the integral, say 0 to B. You defined what B was, you can use it. Often, or at least in the past, they have had like, say, 3 free response problems where all 3 of them you had to write this number down. It gets tiring writing a bunch of digits, and you don't want to screw up writing the digits because we've all done that. So it's best to write it down like one time and give it a letter and then just use that letter. Just to make sure that you're using a letter that isn't already in the problem. Then, on top of that, how many times have you written an equation and written it wrong on a test at some point? Yes. So, avoid that by using the names that are given to you. 99% of the time, they give you names of these functions. If they don't, you could make up your own names and use them. Just make sure that whatever names you give them, they are not already within the problem. But you have to put a proper definite integral down. Then all you have to do is say the answer that your calculator gives you. And you're done. So how can you do this in your calculator? You can do it from your home menu or your graph menu. If you do it from the home menu, you don't have to worry about the window of your graph. If you use your graph, it's only going to solve one integral. So you have to create a third function that is the integrand. So let's see if you can see it. I've got a y1 minus y2 for my y3. And if you remember, that's using the vars button that is located right here. If you click on vars, you go vars, y vars, function, and then just push enter. Minus vars, y vars, function, enter on y2. Then select only the y1 minus y2. So I do that by putting my cursor over the equal sign. Using my left-right arrows, I push enter. Suddenly it's highlighted. I want to deselect the other two, so I'm going to go up and push enter on those equal signs. But when I graph it, I need to be able to see the entire region in the window, or I'm going to have to change my window before I can do anything. So you might get lucky, you might not. La, 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 la. Okay. So I got lucky because I can see the entire region right there. And now what I can do is the special menu, which is the second button and then the F4 for the calculate menu. So second and then the F4. Dink, dink. And you see integral on the list. So you can just push 7 and it's ready. Now, here we go. It's asking for a lower limit. So I'm just going to literally type 0, enter. Then it's asking me for an upper limit. I can use the letter that I chose. I chose the letter B. So I'm going to push the alpha button, if I can see it. I'm going to push the alpha button and then the letter B and tell it, yep, that's the one. Push enter, and voila. And it tells me the answer, and I just need to make sure that I write 3 digits after the decimal point. So I am getting 1.18. Oh, wait, sorry. I'm writing the x coordinate. Yay, we did it. 0.785. If you want to put more digits, you can. They will only read the first 3 after the decimal point. So that's how you do it through the graph. You can also do it through the main, the home screen. So if you push second quit and go to your home screen, then the math button right here, click the math button, click, push the math button, and then FN int is number 9, so I'm pushing 9. And then I'm going to put in my 0 to B. So I push alpha, B. Then when I go to write the integrand, I want to save my time and use vars. Now, pretending that I didn't put a y1 minus y2 in for my y3. Because if you're using the home menu at this point, you didn't do that, most likely. You're just going to go vars, again, like we did before, vars, yvars, function, and then y1, minus vars, yvars, function, y2. And then finally, oh, my microphone fell. I just realized that. Finally, put the x for the dx and push enter, and voila, same number. Sometimes it's easier to use the home menu because it takes time to type in this other function, but then you also have to make sure that your window shows the entire thing before you can use the integration abilities. So there you go. Woohoo! Onward. All right. Sometimes you are asked to find area between two curves, but they intersect while you are within the intersection or within the X range that you're working with. Now, technically, if you just absolute value their difference, that is going to find the correct area. If you have to solve this without a calculator, you're gonna have to sit there by hand and find the intersection points. So I'll just put C1 and C2. You have to find those individual intersection points. And we learned in the last chapter how to integrate absolute value. You have to joyfully set it up as a sum of integrals. And the way how this drawing is shown, f of x is the pink or reddish So it is the top function when I'm in region 1. But in region 2, G is the top function. And when I hit region 3, they swap back. And unfortunately, I can't just integrate for the same integrand one section. Yeah. And then, go about your business of integrating. So the example that your textbook gives is this. So let's, no calculator, draw. And I'm trying to give you a little bit of time to be ahead of me and try to draw these graphs. I'll give my dog a little bit of attention.
Hi. Who's a cute little puppy boy?
Yeah, I should realize my mic is on. I set up markers to try and draw, but wait, no. And again, it's not about being the best artist. It's about you being able to, through your drawing, understand what integral you need to set up. We're going from x equals 0 to x equals pi over 2. And it helps to draw vertical lines between the functions to be very clear to yourself about what the regions are. Now, had I drawn this well, actually, maybe I should, well, I think it'll show the answer if I go over there, but had I drawn this well, you would see that these two regions look identical, just mirror images of each other, and they are. But first, let's just talk about how would you set this up without absolute values, because the AP test does have a multiple choice section where they might just say which of the following integral expressions finds the area of this region. You need to know proper setup. They intersect at pi over 4. And when I am going from 0 to pi over 4, the top function is my cosine. And then I add to that the integral that I get as I go from pi over 4 to pi over 2. And they swap, and sine is now the top function. And I'm going to go through integrating just one of these and doubling it to save a little bit of time, because I'm sure you can do the whole thing if you had to. So this is where it gets frustrating. Integral of cosine is not a cos, so I keep it as is. When I integrate sine, I get a cos, so I change its sign. That's how I remember. That's what I say in my head. When I plug in pi over 4, both sine and cosine are root 2 over 2. And then when I plug in 0, the sine of 0 is 0, cosine of 0 is 1. So I end up with root 2 minus 1, and then the whole thing is going to be double that. I'm just saving time by doing that. And then your textbook goes through and shows the whole thing also. And I'm going to scroll over to that. So know that you can go over to your textbook and find all of this, and it shows the second integral being done as well. And pretty pictures that are drawn. How do you know not to include the middle part? I see. So that would be, let's go back and read the problem carefully. It says, find the area of the region bounded by those two curves between a specific set of x coordinates. So they're wanting you to recognize in between the two functions. And that's why I drew vertical lines between them. So that that's what they're always asking for. It's just a matter of knowing what they mean when you read it. Can you shade the rest of the possible area if you...
Like, could you continue, like, to show, like, where else would the area possibly be so we can visualize it? Like, in that picture? You know what I mean?
Oh, you mean if we kept going?
Yes.
Okay, got it. Hopefully that helps. So what I'm doing is I'm just putting my pen on one of the functions and drawing a vertical line toward the other one. All right. Now that we're having so much fun, it's time to go sideways. Yeah! Woo! Woo! Now, I want to tell you how important this is. You have spent your whole life looking at functions as x is the input variable, y is the output variable. Therefore, the vertical line test determines if it's a function or not. The definition of function is just that you have inputs and outputs, and for each of your inputs, it only attaches to one output. That's all there is to it. And it didn't have to be chosen that horizontal was input and vertical was output. Could have been chosen the other way around.
Wait, so could you solve these problems by basically switching the x with the y?
Well, in this situation, yes, you could, and I've seen people do that. This is wanting you to change your perspective. And while you can change the x's to y's and the y's to x's and go forward as if that were your situation and you would be correct. If you are planning to go through multivariable calculus, you want to get used to dealing with different perspectives. When you hit multivariable, you not only have x and y, but you also have z. And then you have all the duos of xy, xz, yz, and different ways of choosing whose input, whose output, along with issues of sometimes it's a two-dimensional input with a one-dimensional output. Sometimes it could be a one-dimensional output with a two-dimensional. You get what I'm saying? There's so many different perspectives, and you have only dealt with one perspective. which is a little bit dangerous because all of a sudden you hit multivariable and you have to expand your understanding visually very, very quickly. If right now you can get yourself to start seeing things from a different perspective, it will help you a lot. Also, if you are planning on going all the way through the calculus sequence and doing multivariable, I highly recommend that before you do that, you play with some kind of three-dimensional drawing program. It makes a huge difference. I have watched people come into a third semester calculus class and seen people who are incredibly good at calculus. They understand what's going on, but have not had to deal with visually thinking three-dimensionally. It's a challenge. And it's not the calculus itself that is the challenge, it's the visualization and being able to understand what's going in and what's coming out. So I highly recommend that you spend some time. There are a lot of three-dimensional drawing programs out there. Find something and play around with it. And what is it that I'm trying to remember the name of the program robotics uses? You guys learn, I should know this. You guys know what I'm talking about, right? There's a program that you guys learn to use. CAD. CAD drawing. Our school has a license for it. And it's really, really valuable. Anyway. Oh, really? Tinkercad. Okay. There you go. Tinkercad, free, easy to use. I really recommend that you play around with it because it's crushing to a lot of people because you spend way too long with one perspective and then you're all of a sudden expected to expand your horizons on how you view things. Every time you add a dimension, think about how much insanity you add. When you had just like, hi, I'm a pretty little number line. I've got little x coordinates. And then all of a sudden you started drawing 2 dimensions. How much more complicated that made things. Now imagine bringing a 3rd dimension in and how much more complicated that becomes. And how crazy is it to go to from 3 dimensions to 4 dimensions? So I highly recommend that you play around with some 3-dimensional programs. Anyway, so this time we are focused on the right x coordinate minus the left x coordinate instead of the top y minus the bottom y. And there are a lot of things to be cautious about. So here comes an example. And I'm in the 5-minute category, so I got to get moving. So we've got area enclosed by y equals x minus 1. And then you want to work with graphing parabolas from the side. The vertex of this parabola is x coordinate -3, y coordinate 0. And it opens to the right. And you can see we have 2 intersection points. Now, You do not want to find area this way. I don't know if you can tell how much of a nightmare that is. This is the nightmare. If you insist on going this way, you have to solve for y in terms of x, which means you get a plus or minus square root. And also, the bottom function changes from region 1 to region 2. So you have to set up two separate integrals, add those answers together. And when you set up this one, you're awkwardly using the same quote function, but in this perspective, it's two separate functions. This is not fun. But horizontally, if you draw a horizontal line, you've got a right and a left, and it's one integral. But it's very important that you understand the things that are different. When I take a rectangle on its side, I am no longer having differential dx. I am having my width be represented by dy. Because this is dy, the lower and upper limit on your integral must be y values. You need to find the y coordinates of intersection. Also, a horizontal distance is a subtraction of x. It is the right x minus the left x. And in order to find those, you have to take both of these equations and you have to isolate x with respect to y. So for this one, I need to subtract 6 to the y squared and then divide by 2. For this one, x is equal to y plus 1. And then when you draw it, you need to see, okay, the right side is x minus 1 minus the left side, which is x equals, oops, I just wrote it wrong too. I just showed you how easy it is to screw up. I set it up and everything and still wrote the wrong thing. It is very easy to do. I avoid the mistake if I force myself to say the x. I need to take the right x, what is x equal to on the right, and what is x equal to on the left. Then I need to find these y coordinates of intersection. I can do that with a little bit of substitution. So I have y squared equals 2x plus 6, and x is y plus 1. I'm doing this a little bit quickly. Set it equal to 0, do all the lovely factoring. And I can see that positive 4 and negative 2 for the y are my intersections. From there, solve like normal. You've got your definite integral set up and you're ready to go. So make sure that you understand that when you go with these sideways rectangles, your width is dy. The limits are values of y, but this time the length of your rectangle is a right x minus a left x. All right. That was good fun for today. Tomorrow, we go three-dimensional. However, we are very restricted in single variable calculus as to what we can do. We don't get to use all 3 dimensions any way we want. But that's a little sneak peek of tomorrow. Have fun at lunch or eating lunch or having a